It always makes that noise when I start recording lately. I don't know why, just for a minute. All right, so we are getting into, like I said, rational functions. We did the refresher yesterday, just on the basics, with what the parent function looks like to start and basic transformation rules. So when your rational function is given in that format where you can identify A and H and K, you can easily graph that and get your domain and range and asymptotes. But when your graph or your function is given in the format of one polynomial over another, okay, so that's what this format is. We're going to identify what all these different letters represent, what this means, because it looks pretty complicated, but we're going to break it down. So I'm going to be doing some color coding here. All right, so first of all, f of x is what we're calling the function. Okay, it is a rational function, so it is a fraction. So you're going to have a numerator and a denominator. Okay, so we're going to call the numerator's equation n of x and the denominator's equation d of x. N of x is just the function in the numerator. And d of x I don't know why that's so thick. Hang on. Is the function in the denominator. Now, both the function in the numerator and the denominator are both polynomial functions. Okay, now, so when we break this down, this is just the format of a polynomial. What we tested on last unit, unit 5, was polynomials. Thank you. Okay. So with the polynomial function, the polynomial format, remember you've got a leading coefficient and then you've got your degree. Those were two terms that we learned. We learned degree, that's the highest exponent, and then the leading coefficient is the coefficient in front of the variable. So this is your leading term, okay? And then it progresses, because when we have it written in standard form, we have the highest degree first, the highest exponent, and then, so like, let's say this was x to the 4th, then this next term would be your x cubed, if there was one, and then x squared, and then x, and then your constant. Y'all remember that from polynomials? So that's all this is. We've got one polynomial over another polynomial. So in the numerator, we use n for the degree. Okay, so n is the degree of the numerator. And since we're going to have two different degrees, we're going to have a degree in the numerator and a degree in the denominator, we have to use a different letter. So we use m. So m is the degree of the denominator. Okay, and then the coefficient, same thing. We're going to have a coefficient, A is going to be the coefficient in the numerator. See if you can see A. Can you see that yellow okay? Okay. So this is the leading coefficient of the numerator. And then we'll use B is the leading coefficient of the denominator. All right. So those are the different letters you'll see, the different formats that we're going to refer to in these notes. And that's what all those pieces mean. Okay, so we have the leading degree of the numerator and denominator and the leading, or not the leading degree, excuse me, just the degree, and then the leading coefficient. Okay, and we'll just use capital N of X will be the numerator's function and capital D of X will be the denominator's function. Now, there are asymptotes for rational functions. We reviewed those yesterday. There can be vertical asymptote, horizontal asymptote. Okay. We're going to start with talking about the vertical asymptote. So your vertical asymptote happens where the denominator, the entire function of the denominator, equals 0. Okay, so your vertical asymptote is happening at the zeros of the denominator. I think, did we use pink for that? So anything that makes the denominator equal to 0, that's going to be a break in your domain. So it's going to most likely be a vertical asymptote, but it could be a hole, which we're going to talk about in a little bit. Okay, but if your denominator equals 0, whatever value that would make your denominator 0, there's going to be a hole there. So a vertical asymptote there. So you set the denominator, d of x, equal to 0 and solve to find out what the vertical asymptotes are. So when it's not in that format that we were talking about yesterday, where you can just see x minus h, and then your plus k on the outside. When you can't just see that, if it's set up as a polynomial function, you just set it equal to 0 and solve. So this is like what we tested on for polynomials. You may have to factor if it's not already factored. Okay, so we know our different types of factoring. That's what we just tested on with polynomials, is finding the zeros. Now, horizontal asymptotes are going to happen I guess there's not a specific color I can use here because this kind of incorporates, what did I use for degrees? Blue and purple. Okay. I'll use like a dark blue here. Okay, so your horizontal asymptotes are going to come, we're going to find those and determine where the horizontal asymptote is, if there is one, based on the degree of both the numerator and the denominator. Okay, so we're going to compare N and M. We're going to identify and compare N and M to find where's the horizontal asymptote. And it says right here, it has one or no horizontal asymptote. There will not be more than one. Vertical asymptotes, you can have more than one. Horizontal asymptotes, one is the most you can have. Now, when I say compare, we're comparing which one is bigger, N or M. Okay, so here's the three possibilities. N can be less than M, N can be equal to M, or N can be greater than M. Okay, so if N is less than M, so if the degree in the numerator is greater than the degree in the denominator, or excuse me, is less than the degree in the denominator, y equals 0, the x-axis. That's when N is less than M. when they are equal, you're going to compare the ratio of A to B. You're going to look at the leading coefficients. And that ratio, A over B, is going to be your horizontal asymptote. If N is greater than M, so the degree in the top is bigger than the degree in the bottom, there is no horizontal asymptote. The horizontal asymptotes are what determine the end behavior of the graph. So what is the left hand and right hand sides of the graph doing? They're either going to be approaching the asymptote if there is one, or they'll be going up forever or down forever. So with polynomials, we did the leading coefficient test. We said, is the degree even or odd? Is the coefficient positive or negative? And we figured out our end behavior, right? So with a rational function, we're going to do this comparison to see, is there a horizontal asymptote? That is our end behavior. Horizontal asymptote guides the end behavior. So if this is one of the cases, there is a horizontal asymptote either at 0 or at A over B, whatever that is, that's your end behavior. The limit as x approaches infinity, y approaches whatever the asymptote is. The limit as x approaches negative infinity, y approaches whatever the asymptote is. Does that make sense? So the only case when that wouldn't be is what about when there's not a horizontal asymptote? Then how do I know about the end behavior? So to determine the end behavior, when that degree in the numerator is bigger than the degree in the denominator, you then have to look at just those leading terms that I'm going to do an example over here. If I have, let's say I have 3x to the 5th plus 2x squared over negative 2x squared. Let's say this is my rational function. When I look at this, I see N is 5 and M is 2. Y'all agree? So N is greater than M. All I have to worry about, this is going to behave the same. It's going to act like 3x to the 5th over negative 2x squared. Essentially, I don't care about these terms over here is what it means. When I'm just trying to figure out end behavior, I can ignore any other terms besides the leading terms. I only care about the leading terms to figure out end behavior. Now, in this case, that would reduce to what? What do you do when you're dividing the like bases, x over x, but they have different degrees? Do y'all remember what you do with that when you're dividing? You subtract. So what's x to the 5th over x squared? That's an x cubed. Now, does the 3 over negative 2 reduce? No, so it's just going to stay negative 3 over 2. Now that looks like a polynomial, doesn't it? So now can I do the leading term test that we did on the last test we just took for polynomials and say that this degree is odd. And this leading coefficient is negative. So what's the end behavior going to be? If it's odd, they're going in opposite directions on the left and right, correct? Okay, and if it's negative, it's a reflection of the parent function, right? So it would be this direction, like this. So this rational function, this is not the graph of the rational function, no. But this end behavior is going to act like this end behavior. The left side is going to go up and the right side is going to go down. Does that make sense? So when n is greater than m, there is no horizontal asymptote. So to figure out your end behavior, you just need to look at the leading terms. Reduce. And find end behavior. Based on that, like what we just did. We looked at just the leading terms. We reduced it, and it's a polynomial. And we know how to do polynomial leading term tests, right? We feel okay about end behavior based on horizontal asymptote? Okay. All right, so then there's this graphic. This is just pulled straight from your textbook. It's kind of just a reference. So your vertical asymptotes, we did talk about this yesterday, are going to be written as x equals a number. So remember to write your asymptotes as equations. Horizontal asymptotes are going to be written as y equals a number, if there is one. Okay. And those guide the end behavior. Horizontal asymptote guides, this is end behavior as x approaches negative and positive infinity, right? Now here, we'll get into this a little bit later, but your vertical asymptote isn't affecting the end behavior, but it is affecting the behavior of the graph as the graph approaches that asymptote. So you may remember last semester when we were talking about limits and continuity, we did this. We said as x approaches a specific number, and then we did the little minus was from the left, or the little plus was from the right. So your vertical asymptotes will affect the behavior around that at a specific number, but the horizontal asymptote affects the behavior at the ends when x is going to positive and negative infinity. Cool. That's something I might add up here, just where we are talking about asymptotes. We write vertical asymptotes as x equals a number. We write horizontal asymptotes as y equals a number. Don't just give a number, it's an equation. It's a vertical or a horizontal line. So it needs to be x equals the number for a vertical line because it's going through the x-axis, or it needs to be y equals a number for the horizontal asymptote because it's going through the y-axis. Good? Okay, so let's try some examples here on the back. We want to identify vertical and horizontal asymptotes. So the first thing for A is going to be, the first thing for all of these I'm going to do is set the denominator equal to 0 to find the vertical asymptotes. So the vertical asymptote, we said, comes from set the denominator equal to 0. So for vertical asymptote, I'm going to set d of x equal to 0, which in this case, d of x is x squared minus 1. Bless you. So how am I going to solve this for x? What do I need to do? Okay, so I'm going to add the 1 over, so it becomes x squared equals 1. Then what am I going to do? I'm going to take the square root. What am I going to remember when I take the square root? That's extremely important. Yeah, the plus or minus. If you don't remember to do that plus or minus when you're solving this way, you're going to lose one of your solutions. You're only going to put 1 when it really should be positive or negative 1. Square root of 1 is 1, right? But it should be positive or negative 1. Okay, or this was also a difference of squares. Okay, remember I could have factored this into two nearly identical binomials. The square root of x squared is x. The square root of 1 is 1. And you do 1 plus and 1 minus, right? And then you would set each of those individually equal to 0. And you would get negative 1 when you move that one over by subtraction. And you would get positive 1 when you move that one by addition. So see, it doesn't matter which method you used, as long as you remembered that plus or minus, you got both of the solutions, right? All right, so those are my, we said we write them as equations. So x equals negative 1 and x equals 1. Those are my vertical asymptotes. Now my horizontal asymptotes are going to come from comparing n and m. So we said degree of the denominator and the degree of the numerator. So in this case, n is 2 and m is 2. So when I compare them, it's an equal sign, isn't it? N is equal to m. So what do we do in that case? When n is equal to m, we have to look at the ratio of a to b, right? So in this case, now we need to identify those as well. So a is the leading coefficient 2. And b, what's this understood leading coefficient if nothing's there? It's an understood 1. So this is 2 over 1, which is just what? So y equals 2. Remember, we write it as an equation, is my horizontal asymptote. This process makes sense? All right, let's do the same thing for b. Now in b, when I go to set my denominator equal to 0, it's just a linear function. So that one is easy enough to solve. I'll just subtract the 1 over. Now they're using t instead of x. So if you want to leave it as t equals negative 1, that's fine. If you prefer to write x equals, that's fine too. But that's the variable they're using. So that's the there's only one vertical asymptote here, because that's the only value you could plug in, and it would make the denominator 0, right? Y'all agree? Okay. All right, then we need to compare n and m. So the degree in the numerator is 2. If there is no exponent there on the variable, what does that mean? The understood power is power of 1. So when I identify n as 2 and m as 1, that means my comparison, n is greater than m, right? And what does it mean when n is greater than m? There is no horizontal asymptote. Now, they didn't ask about the end behavior, But you could go ahead and tell me, I'm going to go ahead and do this just for the practice of it. When there is no horizontal asymptote, we can figure out the end behavior, because this would behave the same as t squared over t to the 1, which reduces to just t, right? That's just a linear function, a positive. So it's an odd degree, a positive coefficient. So this would be the end behavior, wouldn't it? Rise on the right, fall on the left. So if they asked about the end behavior, I would say the limit as x approaches infinity, or you could use t, since they used t, you could say t approaches infinity. And they called this function g of x. So the right side is going up, so it'd be infinity. And the limit as x approaches negative infinity, that's the left side, is falling, so it'd be going to negative infinity as well. Okay. On C, we've got our denominator, oops, got to be red, is s squared plus 1. We set it equal to 0 and solve. Now, when I try to go and solve this, I get -1 when I move it. And then when I try to take the square root, what do you notice? Yeah, we're trying to take the square root of a negative. Are you able to do that? We cannot. Square root a negative number. What this is telling us, the fact that we can't solve this when we set it equal to 0, it's telling us there is no vertical asymptote. Remember, a vertical asymptote is going to happen where the function's denominator would equal 0. There is no number that we could plug in here and get a 0, is there? Because no matter what we plug in, we're going to get a positive number, whether we plug in a positive or a negative, right? And then we're going to add 1 to it. Or if we plug in a 0, we're going to get 0 and add a 1 to it. There's no way this is ever going to come out equal to 0. So that means there is no vertical asymptote. Okay. Now for the horizontal asymptote, we're again comparing n and m. So m is the 2 because s is squared down there. But in the numerator, s is to the 1 power. Understood, 1 power. So n is 1. M is 2. So when I do my comparison, n is less than m. What did we say when n is less than m is going to happen? You can look back. Yeah, y equals 0 is the asymptote. It's just the x-axis. Okay, so there is an asymptote, but it's just at 0. And so if I was asked for the end behavior here, the limit as x approaches infinity would be 0. The limit as x approaches negative infinity would be 0. Okay, if I had asked for the end behavior on part A, it would have been 2. As x approaches infinity, y would be 2. As x approaches negative infinity, y would be 2. Remember, if there's an asymptote, that's your end behavior. That's where your graph is going on both the left and the right. You feel okay about vertical and horizontal asymptotes? Okay. Let's see, what do we have time-wise? Oh, we got time. All right, so the next thing we're going to talk about are holes. Okay, so when we look at our function, sometimes there will be a factor in the numerator and in the denominator that's the same. Because if we look back up here, notice this said asymptotes of a rational function, okay, And then it said the asymptotes are going to happen when n of x and d of x have no common factors. Okay, so when we factor the numerator and denominator, there's nothing in common. However, if there is something in common, so when they do have a common factor, that means there's going to be a hole in the graph. Okay, so here's the process. I don't know. I guess I'll use green. I don't remember what I used green for, but the process for a hole, we are going to factor the numerator and the denominator, okay, to see if anything reduces, to see if they have something in common, okay? So if any factors reduce, that means if they have anything in common, there is a hole. What you'll do is you'll set the reducing factor, that's the factor that they had in common, equal to 0 and solve. What you get, that's the x value of the hole, because the hole is a coordinate. It's a single point that's been removed. We talked about discontinuities last semester. Remember, a hole is the removable discontinuity. It's just one point taken out. It's graphed as an open circle. So this will find us the x value of that coordinate, of that hole. Then we plug that x value into the new equation after we've reduced, okay, and solve for the y value of the hole. Okay, so holes aren't, I'm not going to say those are common, but if you have a common factor, that is what it means. It means that there's a hole in the graph. So for instance, what we talked about a second ago with our asymptotes. So I'll make a little side note up here in this space that I have. If we can make the numerator 0, but the denominator, if a number that you plug in makes the numerator 0, but not the denominator, okay, then that is what we call an x-intercept or a root. But if there's a number that we can plug in and it makes the denominator 0, but not the numerator, that's where we're going to have those vertical asymptotes we were just talking about. Anything that makes the denominator 0 is a vertical asymptote. That's what we said, right? But what we're saying now is if it's a number that you plug in and it makes both the numerator and the denominator 0, that's a hole. Does that make sense? So if it makes the denominator 0, it's going to be either a vertical asymptote or a hole. How you decide is, does it also make the numerator 0 or not? So let's try this. We want to identify horizontal asymptotes and determine if there's a hole and or vertical asymptotes. So we first are going to, I'm going to factor. In my numerator here, I can factor, this is a difference of squares. Difference of 2 squares. So that's going to factor to the 2 nearly identical binomials, right? What's the square root of 9? We're going to do 1 plus and 1 minus, right? And then my denominator is x plus 3. So is there a common factor here? The x plus 3. That can reduce. That tells me there's a hole. So I know there is going to be a hole. And it's going to happen where that factor, x plus 3, equals 0. So when I solve that, I get -3. Y'all agree? So that's the x value of the hole. Now the new equation, when I reduce that, what am I left with? It's just x minus 3. So that's what I mean when I say the new equation. So x minus 3, we're going to take -3 and we're going to plug it in. So we have -3 minus 3. I guess I should write y equals here. That might help it make more sense. Okay, and we're going to get -6. So that's the y value of the hole. So the hole is at -3, -6. Does that make sense? Now, is there anything left in the denominator when I reduce that? It's an understood 1, right? So is there anything else that could make the denominator 0 besides the -3? No, because there's not a variable there anymore, right? So that means that there are no vertical asymptotes. There's nothing else left that could make the denominator 0 except for what would also make the numerator 0. Okay, so there is a hole, but there's not a vertical asymptote. Okay, or yeah, not a vertical asymptote. Now the horizontal asymptote, we said, comes from comparing n and m. You're comparing n and m of the new equation. So in the new equation, my n is an understood 1. Y'all agree right there? But in the denominator, there's no x at all, right? So what that means, that's an understood x to the 0 power. If there is no variable, anything to the 0 power is 1. Do y'all remember that rule? So if there is no x in the denominator, that means m is 0. So that is n is greater than m. So that means what? There is no horizontal asymptote. So this has no asymptote, vertical or horizontal, but it does have a hole. Okay, let's check out E. We're going to factor both the numerator and the denominator. Okay, so quadratic form trinomial here. X squared would factor to x times x. And then the only factors of 2 are 2 and 1, right? And I need 1 positive and 1 negative so that it multiplies to a negative. But I want them to add to a positive 1. So I want the 2 to be positive and the 1 to be negative. We're going to factor the denominator. Factors of 6 that would add to 1 are going to be 3 and 2. And again, I need 1 positive and 1 negative so that it multiplies to a negative, but I want it to add to a -1. So I want the 3 to be negative and the 2 to be positive. So is there going to be a hole in this one? Yeah, because you've got x plus 2 in both the numerator and the denominator. We'll finish that one up tomorrow. The bell's about to ring.